morning, students. So now let us talk about equipotential surfaces. So as the name suggests over here, equipotential. Equi means the same, potential. Potential is same. If the potential is same everywhere on a surface, then that surface is known as equipotential surfaces. So before knowing this, we'll get the clarity about the potential difference. So potential difference, how to define that potential difference? It is defined as, suppose there are 2 points A and B. There are 2 points in a space, we can say A and B. Now I am moving a charge, positive charge, a unit positive charge from A to B along this line. So to do this along this line, again is the electric force. I am bringing the positive charge, a unit positive charge from A to B along this line, again is the electric force. Then this work done is known as potential difference between A and B. So mathematically that expression gives as potential difference between A B is known as VA minus VB, which is equals to minus of integral E bar dot dr bar from A to B. So here the negative sign indicates that as electric field intensity increases in a particular direction, in that direction the potential decreases and vice versa. Which means ఏ డైరెక్షన్లో అయితే ఫీల్డ్ ఇంటెన్సిటీ ఇంక్రీజ్ అవుతుందో ఆ డైరెక్షన్లో పొటెన్షియల్ డిక్రీజ్ అవుతుంది, అండ్ ఏ డైరెక్షన్లో ఇంటెన్సిటీ డిక్రీజ్ అవుతుందో ఆ డైరెక్షన్లో పొటెన్షియల్ ఇంక్రీజ్ అవుతుంది అనేది దీని యొక్క మీనింగ్గా తీసుకుంటున్నాం మనం, రైట్? So here the work done against the electric force can be given as, so here I am moving a charge against the electric force. So the work done expression for work done is given by work done from A to B against the electric force is given by Q into VB minus VA. But what is VB minus VA? This is VB minus VA, right? So minus Q integral A to B E bar dot dr bar. So since a charged particle is a constant, I can bring this constant into the integral. So this is written by integral A to B QE bar dot dr bar. And we know this QE bar is nothing but the force experienced by a charged particle when it is placed in electric field. So this can be written as from A to B F dot dr bar, which is very fundamental relation between work done and force. Okay, so here in this case, as we are discussing about the electric field intensity and electric field, something like that, so the force involved here is the electric force, isn't it, right? So here for uniform electric field, VA minus VB is equals to E times into T. So the uniform electric field can be represented like this, which means everywhere the field intensity is the same. In fact, these field lines are due to a particular charge somewhere over here, a charge giving the field and in this direction. So the all field lines are in the same direction, and everywhere the field intensity is same like this, right? So for this, the expression for the potential difference is VA minus VB is equals to ET. For non-uniform electric field, Va minus Vb is equals to integral over E dx. It is very clear that here we are taking that a different integration as the field varies every time. So every point at a dx, we would like to calculate the E value, and we are adding from A to B, which gives the potential difference between A to B. So here I can say Vb minus Va is equals to minus Et. By simply saying, this is very simple expression we can remember always, right? And coming to the next one, okay, now based on the knowledge of the potential difference as we discussed in the previous case, so here we discussed about the potential. Now we would like to get the idea of the equipotential surface. Here I am giving, if I am considering a electric field intensity like this, by just seeing it is very clear that the field here is uniform electric field. Okay, now if a charge is shifted from point A to point B on a surface, let it be there is a surface, so the charge is moving from here to here. See here, the movement of the charged particle is perpendicular to the direction of the electric field. If the particle is moving in this direction, but the field is moving towards my right, so the work done in shifting will obviously 0, as electric force is normal to the direction of the displacement. So here it is the relation between E and F, right? F dot Q, something like that. So here the force is perpendicular to dr, so the field intensity is the direction of field intensity, so that is 0. So I can say once again, so here the particle is moving perpendicular to the direction of the electric field. The work done becomes 0. Work done becomes 0. Hence, since theta is over 90, right? So theta is 90 here. The force applied on the particle is perpendicular to the displacement of the particle. Then the work done is 0. As no work done, we can say the potential difference can be 0, since there is a relation between work done and potential difference. Did you get my point? I think so, right? So here the particles, the points which are lying on the line, AB, all are having the same potential, we can say. Then the surface M is known as equipotential surface. Got it? So here I am writing the same thing what I am saying right now. So the work done in moving a charged particle along AB as shown is 0, since work done is 0, both A and B have same potential. Therefore surface M is known as equipotential surface. Okay, right. So here I would like to give the idea of the spherical equipotential surface due to a point charge. Let it be this is the point charge Q. So the field lines, here I am taking the positive charge, so the field lines are radially outwards at every point here I am taking. So the equipotential surfaces are spherical around it. So the dotted lines gives the sense of the equipotential surface, which means if there is a charged particle placed on any circumference of the circle over here, and I am moving the particle from here to here, maybe half of the circle or full circle, or making an arc like thing. So the work done to bring a charged particle on this surface, work done to move a charged particle on this surface, so the work done becomes 0 since all the points are having the same potential on it. So to give a much clarity regarding the equipotential surface, I am considering the gravitational field. So assume that this is the surface of the earth. So at first neglect the surface of the earth here. We are all lying on the earth, right? No doubt. Here I am taking a bench and a book is kept on the bench here. Let it be, this is the book, a heavy book like physics book. So the book now can be displaced from here to here. So let it be, this is point A and this is point B. There are infinite ways of the movement of the book from here to here. So one is the shortest possible path is along the surface of the bench, or I can move the book vertically upwards first, and then like this, and then like this. For our convenience, I am taking only the straight lines, or you can take a parabolic path, something like that. Whatever it is, you can choose. And while bringing the book from here to here in this particular direction along the surface of the table, I am simply neglecting the frictional force. So let mu be 0. It is a smooth surface. Consider that. So here I have two paths. This is path 1 and this is path 2. So during this path 1, during the traveling along the path 1, I would like to calculate the work done by the gravity, isn't it? Work done by gravity, not work done by the agent. Agent in the sense, here I am. I would like to calculate the work done by the gravity. So here work done is equals to force times displacement. We know that. Okay, right? So work done, this displacement. What do you mean by displacement? In calculating the displacement, we are taking only the consideration of the initial point and final point. So everywhere the gravitational force is same here or here, because both are lying at the same height from the ground itself, isn't it? Let it be, this is the radius of the earth, it is the center, and it is certain height h. So both A and B are at the same height with respect to the center of the earth. So both are at the same height, we can say, and the force everywhere it is same since both are at the same height. So coming to the displacement, here also the displacement is the shortest path. Here I am taking, my sense is very simple here. Since A and B are at the same height, the work done by the gravity is 0, because the potential energy at A is equals to the potential energy at B. Careful, here I am considering the potential energy. I just feel that potential energy is related with the potential, isn't it? So since both A and B are at the same height, the potential energy is same, which means the potential is same, which means both A and B are lying on the equipotential surface. On any equipotential surface, if we move the block from here to here, the work done by the gravitational force is 0, since both are lying at the same height. Right? Next, now consider the path 2. Another path, here I am taking the path 2. So while doing so, from A to C and from C to D and B. So from A to C, as height increases, there is a change in potential energy, and again C and D are at the different height, and D and B are at the different height. So every time we are doing some work against the gravity. So during this path, I would like to calculate the work done, and I can say the work done by gravity is not 0. even though both are lying on the same plane, right? So here, while deciding the equipotential surface, we'll just consider the path from where to where it is moving. Okay, this is the best fine example I can say. Thank you. Now let us discuss one small problem regarding the equipotential surface. So the problem is given as a touched charge Q0 is moved without acceleration from P to Q in a uniform electric field over the path as shown. So here they are giving the uniform electric field. So there are 3 points P, Q, R, and a test charge Q0 is moving from P to R, R to Q, and Q to P. So they are giving the distance between P and Q as T, and there is an angle theta over here. Now what they are asking, find the potential difference P and Q. So the particle is first moved from P to R and R to Q and Q to P. So there are 3 steps we can say. So we have the relation such as E bar is equals to minus gradient of V. This can be written as minus of dV by dr, that is equals to E bar, and from this I can say dV is equals to minus of E bar dot dr bar. So this is the key formula we are going to use here. So from the triangle, right angle triangle over here, I can say cos theta is equals to PQ by PR, and PQ is equals to PR cos theta. Of course PQ is the value of D, we know, so let it be, this is expression 1, right? So coming to the first path from P to R. From P to R we would like to calculate the work done, and then R to Q and then Q to P. By just adding all these work done, we can get the potential difference between P and Q, right? So this is the way we have to do. So from P to R, which means from P to R, integral dV is equals to, this is the formula I'm using, and here on integrating both sides I can write the expression such as minus integral of P to R E bar dot dl bar. So here I'm taking the in terms of R, I'm taking the length here over here, right? So by taking minus outside, I'm already taking, so minus integral P to R, I can say E dl cos theta. A dot B is equals to AB cos theta, isn't it? So from this I can say minus E cos theta. Since E and theta are constant, I can say P to R dl. This is nothing but the distance between P and R, right? So this implies minus E cos theta into PR, okay, minus E cos theta into PR, right? So this implies minus E PR cos theta. Can I say? Then what is PR cos theta? PQ. Then what is the value of the PQ from this diagram? D. So this is minus ED. I can say let it be equation 2. And similarly, I would like to calculate the work done or the potential difference such as so here we are, so on the left hand side, on the left hand side I can say VR minus VP. So from R to P, VR minus VP is equals to minus ED, or VP minus VR is equal to ED. There is nothing wrong with that. Now from R to Q, I am moving the particle from R to Q. So as we discussed in the previous case, here the particle is moving perpendicular to the field direction, isn't it? So since R and Q are at the same points, same surface, that surface, you know, the equipotential surface, the potential difference is the same, which means VQ is equals to VR, or VQ minus VR is equals to 0. We can say since both are lying on the same point, same surface, the potential difference is same, right? Therefore, what is VPQ? Can I say VPQ can be written as VP minus VQ based on the previous knowledge we have? So from this I can say VP minus VR, I'm adding minus, and VQ minus VR. Can I say? This is a simple mathematical relation. I'm just adding plus VR and minus VR. You can multiply this one, minus into minus VR, VR will get cancelled. Then what is VP minus VR? Here I am having, sorry. So VP minus VR, here VP minus VR is ED, simply saying. So ED minus, what is VQ minus VR? 0. This implies 0. So potential difference between P and Q is simply E into D. This is the most important point you have to remember always here is, irrespective of the path followed by the particle over here. So the work done to bring a point from one point to another point is simply depending on the initial point and final point, right? As we say in terms of the displacement vector, right? Thank you.